This problem is an improper integral for a couple of reasons. One is if you have x equal to 0, that is going to cause division by 0. Also, the natural log of 0 in itself is undefined. As a limit, it equals negative infinity, so we've got a couple of problems to overcome. We can use the calculator to estimate and see if we're going to be getting a finite answer or not. So natural log of x divided by the square root of x, and it's from 0 to 1. So change the window, say from -1 to 2. So the area we're talking about is down here, so it's going to be negative. And then if we estimate, so calculate the integral, and I can't use 0, so I'll use something close to 0. And then 1 is not a problem. So it turns out that area is approximately -3.4. So with a number like that, my guess is that the answer might be like -3.5, maybe as much as -4, but I wouldn't imagine that it would go to negative infinity. Alright, now we need to actually integrate this thing. So if we, since I've got two functions, I'm going to use the integration by parts. I'm going to look at it as the natural log function multiplied with x to the -1/2 function. And while I'm integrating, I'm going to leave the limits off and replace those in the end. So with this, so the u should be chosen so that du is an easier function to deal with. So this should probably be the u, and this will be the dv. So if we have u is equal to the natural log of x, and that dv is equal to x to the -1/2 dx, then over here take the derivative, and that's going to be 1 over x, which is actually easier to integrate than the natural log function. And over here find the antiderivative, so add 1 to the exponent, it will become a +1/2. And then you need to divide by that +1/2, or in other words, multiply by 2. So integration by parts is going to go u times v. Let me continue over here. So we'd have u times the v, so that's going to be 2 square root of x from this part times the natural log minus the integral of, now multiply these two, so it would have a 2 in it, then it would have x to the 1/2 on the top and x to the 1 on the bottom. If you subtract those two, you'll get x to the -1/2. Okay, now we just need to integrate this, which actually we just did that here. And we got the answer that it's 2 times x to the 1/2. So we're going to have this 2 radical x natural log of x, and then minus, this has a 2 in it, and when we integrate x to the -1/2, it's going to have a 2 in it, so that's 4, and then it's x to the 1/2, which means the square root of x. Okay, now evaluate from 0 to 1. So let's see, substitute a 1. This would be a 1. Natural log of 1 is 0, so that's actually a 0. And then substitute a 1, we get -4. So I have a feeling that's what the answer is going to be, based on that graph we looked at earlier. But we still need to substitute the 0. So minus, when you substitute the 0, this is going to be 0. This, as a limit, is negative infinity. So is the answer negative infinity because this is so powerful, or is the answer 0 because this takes control of the situation? In other words, this one's going to negative infinity, this one's going to 0. Which one goes there faster? That is the point of L'Hopital's rule. So on some scratch paper here, we're going to have to say, what's the limit as x approaches 0? And it's actually on the right-hand side since this is from 0 to 1. So technically we could put, we're dealing with positives. And the 2 doesn't matter. I'm just going to leave the 2 there for a moment because it's really these two that I have to figure out. So then it's the square root of x times the natural log of x. So for this, we then need to somehow use L'Hopital's rule. But the problem is with L'Hopital's rule, it says if you have something divided by something else, and you get the result 0 over 0, or infinity over infinity, you're then allowed to use L'Hopital's rule. So we need to somehow make this into a fraction. What I could do is leave the natural log in the numerator. I could bring this to the denominator if I rewrote it as x to the negative 1/2. Because algebraically, that's the same thing. Once you simplify this, you would get that. Or I could say, well, negative exponent means that it's 1 over that. And I actually need to look at it both ways because in order to use L'Hopital's rule, you need to say I've got infinity over infinity or 0 divided by 0. Well, this is saying 1 divided by 0. As a limit, that's infinity. Natural log of 0 as a limit, that's infinity. So you do have infinity divided by infinity. That means you can use L'Hopital's rule. L'Hopital's rule then says, okay, go ahead and take the derivative here, take the derivative here, and then find out what's happening as x approaches 0. Well, for that, I'm going to use this one, because to take the derivative, it's easier in this form than in this form. So using L'Hopital's rule, I would have the limit as x approaches 0. The derivative on top would be 1 over x. On the bottom, it would be negative 1/2, and then x to the negative 3/2. In order to simplify this, I could move this to the numerator, or in other words, multiply by x to the 3/2 positive. And I could simplify this by moving inverted multiplied by negative 2. Okay, so then we've got, this is 1/2, this is 1, so if you subtract those exponents, it leaves a half. So we have the limit as x approaches 0, there's a negative 2, and there is a x to the 1/2, or in other words, square root of x. So finally, it turns out that it's 2 times the square root of 0, that's 0. Okay, so that means that out of these two, this is the winner. That this function is more powerful than the natural log. It won the battle. So it's 0. So finally we can go back over here and say this part, when we have this, it's going to be 2 times 0. And then minus 4 times the square root of 0, so that's gone. So it turns out that everything is gone except for the negative 4.